Welcome back, everybody. Let's proceed. So just a word of warning for anybody who is watching right now the video rehearsing for the exam. If you're completely lost, just go back one video with the 101 primer on the probability theory. So normally, so I assume that you all knew it. Now I'm aware of the fact that even though it's a third-year bachelor's course, some of you are in your second year of bachelor's. Can you raise your hand if you're in second year of bachelor's? It's a minority, right? But some of you. And for those of you who are in the second year, it might be that you are taking lectures like the database lecture that I referred to last week, or the Wahrscheinlichkeit und Statistik at the same time. So I'll try to keep it in mind, basically, and I hope that what we rehearsed in the last hour was made sense. Just to get an impression, who really, what I presented to you in the first hour, you already knew it and it was easy and you were bored? Very good, that's exactly what I want. Who was scared and wants to run away by all this formalism and notation? Okay, nobody's scared. Okay, so now you can fasten your seatbelt and we can proceed with probabilistic information retrieval. So, just as a recap, we saw the evaluation setup in which, in order to evaluate your system, you have a collection of documents, you have a collection of information needs, and you have a collection of people that you can ask. These are domain experts, and you can give them a document, give them a query in an information need, and you ask them, given that the query returned that document, is that document relevant to the information need, right? And you have the domain expert that says yes or no, right? So again, document, query, yes or no, right, by a domain expert. So that's the yes or no. And so I told you that in the early days where we didn't really have the computing power, the collections were a bit small, so 1,000 documents, 200 needs, we scaled to 2 million documents, 500 needs and so on, and more domain experts, and it starts costing a lot of money. And what I would like to do now is use that not in the context of evaluation, but use that in the context of building a new system, at least come up with the theory, and then we can go ahead and implement it. Now, what we are going to do is a thought experiment. It's a little bit like Schrödinger's cat. You don't actually put a cat next to a radioactive atom and kill it. Of course, nobody would do that. It's just something you do in your head, right? It's a thought experiment. So we are going to have this in mind with our thought experiments, that we have, because now it's in our thoughts, so we can do whatever we want. So we can imagine that we have 1 trillion documents, that we have a million queries, and that we had a heptillion people, right? So imagine that we just can afford that because it's all in our thoughts. And so I would like to map it back to this omega space and the elementary events. So imagine, because it's a thought experiment, so I get to do whatever I want. Imagine that I did find a heptillion people, right? A heptillion people. I have this huge facility in the Antarctic with a heptillion rooms, and in each room there is one of these heptillion people. And in every one of these rooms where there is some person, they are handed over a query and a document, and they have to say yes or no. So in every room, there is a query, there is a document, and there is a yes/no answer. Now, imagine that each one of these rooms with a query, a document, and a yes/no answer is one of these small omegas. So again, a heptillion rooms, a heptillion people in them, and in each one of them, we have a document, a query, and a yes/no. Who imagines that? Okay, it's in our thoughts, right? You cannot do it, but it's a theoretical experiment. And you will see how the mathematics is actually very useful. So this is it, a heptillion people, lots of queries, lots of documents, lots of domain experts. Now that I told you what a random variable is, in particular that it's not random, that it's not a variable, that it's actually a function, when I tell you there is a query and a document and a yes/no answer in every room, you probably thought, okay, these are random variables, because this is a function. It's a function from each room to a query, from each room to a document, from each room to a yes/no answer. So it's a function from omega, the set of my rooms, to some target sets, the set of documents, the set of queries, and the set of Booleans for the yes, no answer. So who agrees that these are random variables? Okay, few raised hands. Okay, so basically, now I can, since it's a random variable, I'm going to be using an uppercase character, and I'm going to call big Q the random variable that assigns every small omega. It's every one of these people in the heptadian rooms. I'm going to assign a query, for example, the query information or the query information retrieval, right? So this is a random variable Q that goes into the set of all possible queries. Then I have another random variable that I call big D, and again, because it's a random variable, so it's a function, that assigns each one of my heptadian people to one document. So the set I have on the left is my collection of documents, right? I could have 1 billion documents in there, and I have basically a heptadian people mapped to 1 billion documents, right? It's of course not injective, right? The same document might be assigned to multiple people and multiple rooms, right? All right. And then we have big R, that is the yes, no answer. That goes into the Booleans, right? It's a yes or a no. So yes means true, no means false. So R applied to any one of these little omegas goes to yes or to no. So it's just 2 elements. It's a random variables with 2 values, the set of Booleans. So these big Q, big D, and big R are absolutely fundamental to probabilistic information retrieval, right? So keep in mind these heptadian people in heptadian rooms and these deterministic functions, D, Q, and R, that assign a query or a document or a Boolean to every one of these heptadian rooms. Now, we are going to assume, of course, that there is some probability distribution over all of the rooms. The easiest is to imagine that it's uniform, right? So we just put a uniform weight on all of the rooms, and it's 1 divided by 1 heptadian, the probability of every room. And then you agree that you can compute the probability if you have these functions Q, D, and R, you can compute the probability that the query is information retrieval. You just add the weights of the rooms in which it is information retrieval. You can compute the probability that the document is this information retrieval book. All you need to do is add the 1 over 1 epsilon over all the rooms such that D of the room is the book. And then you can do the same for R. Actually, it's probability of true, probability of false, right? So you can partition the whole set of rooms into the rooms in which they said yes and the rooms in which they said no, right? And then you get 2 numbers. The probability that R is yes and the probability that R is no. Everybody so far with me? Okay. All we did was instantiate our set omega into these heptadian people in my evaluation facility on Antarctica. But now, do you agree that since I have an omega space with a heptadian elementary events and I have random variables R, big D, and big Q, do you agree that if I take a specific document, small d, D is a mathematical variable, it can be anything I want, so D could be the information retrieval book. Small q, that's also a mathematical variable, so it can be anything I want, so Q could be, small q could be, for example, the query information retrieval. Do you agree that if I take any small d I want and any small q I want, I can write down that thing in here, probability of big R being true, 1 true, yes, it's the same, given conditioned on the big D being the document I want, so the information retrieval book, and Q is the query information retrieval. Who agrees that that makes sense to write down, right? If you take an omega space with a probability measure on it, and you have 3 well-defined random variables, R, D, and Q, and then you take big D and small d and small q to be any ones you want, you can write down that, and it makes sense. You can even compute it, because the way you compute it is very easy. In these heptadian rooms, you take all of the ones that are given the information retrieval book and the query information retrieval. You count how many there are. Then you look at those of them where they said yes, you count that again, then you compute the fraction, right? It's all of the rooms in which R is 1, D is small d, and Q is small q, divided by the number of rooms in which D is small d and Q is small q, right? I can do the simple division because I took a uniform probability. Who is with me? Okay, so this is well defined, right? I get to do that. But again, it's a third experiment. I don't actually have these heptadian people. So at that point, it's all in my head. Okay. So I can even draw a visual in here. If I have the intersection of, in green, green is the intersection that my document is small d and my query is small q. And I look inside what is a yes and what is a no. In that case, there's a majority of yeses for that specific document small d and that specific query small q. And then what I could do is do that for many documents, right? Imagine now, again, it's a thought experiment. Imagine that I have my facility in Antarctica, and then I have somebody sitting in Zurich in front of their laptop, and they are accessing my search engine that I'm building to use my insights with this. And the user in front of their laptop has just typed information retrieval. That's the small q. I want to now return results to that user using the people in Antarctica. So how could I do it? Well, what I could do is compute this probability that it's relevant given document small d, small e, small f, small g. So all of the documents that I have, so I can do it 1 billion times, d, e, f, g, and all the documents. And the query is q because that's what the user just entered, right? So now I have the probability that given that the document is small d, the query is q, it's relevant. The probability that given the document is E, for example, that's a book on, I don't know, butterflies. And then it's relevant. Then I do the same for F, G, and so on. Now, in an ideal world, either it's relevant or not. So if all the domain experts agree in Antarctica, then either they're all going to say yes or they're all going to say no. And all I need to do is pick those documents for which they said yes. So in that case, my query would return 2 documents, which are small d and small e, right? Who agrees, right? Now, you know how it is in real life. People disagree. So if you actually do it, maybe the domain experts in Antarctica will not agree with each other. Some of yes for the same query and document will say, yes, it's relevant. Some others will say no. So with real people in Antarctica, you are going to be getting something that looks more like this. I can still use that for my information retrieval system. I can just sort by the numbers, right? I take the highest quantities. And now I've just invented a ranked retrieval system where I can use that as a score, and I return the ones that have the highest probability of relevance for a given document, and the query that's been entered. Who sees that I just invented a ranked information retrieval system? Right. So if I owned all of the 21 million Bitcoins, and I was the wealthiest in the world, and I would find the heptadian people and put them in Antarctica, I can build a query engine that actually, based on this, is going to return documents to the users. Now it's the real world. I don't have that much money. I also don't have a heptadian people that I can hire. So we need a bit more work here. We need to work with these probabilities here and use the power of mathematics in order to derive something that we can actually implement, right? That wouldn't need this facility in Antarctica. So I have a few more slides to expand on this. Basically, it's a probability that it's 1. You want to return, if you want, so this is ranked retrieval, right? You could also return the Boolean retrieval system, where you just return those for which more experts said it's relevant than non-relevant. So it's a probability that R is 1 is higher than R equals 0, right? Condition on D and Q. So in that case, on the left, you would return the document small d, and on the right, you would not return the document small d, right? You're looking for when there is a majority vote on R equals 1. It's the same to say that you want the probability of R equals 1 to be higher than 1/2. Then you got yourself a Boolean information retrieval system, right? All right. Then you can have fancier stuff. Just quickly, you don't need to understand the details, but you could also have weights. So you could model the costs of a false positive, the cost of a false negative. And then you could say, okay, I care more about false positive than false negatives, right? You could say it's a bigger deal to have a false positive than a false negative. So you can add weights in here and come up with something else that you optimize on, right? Instead of optimizing on this here, you could instead optimize on a fancier formula that has different costs for 0 and 1, right? But if the costs are the same, it's basically based on the costs of a false positive and the cost of a false positive, a false negative. If you take the same weights, you're basically back to square one. You're back to the idea of sorting this by decreasing value. All right. So now I have a thought experiment that is completely not implementable in practice. So we are going to now use assumptions and use the base formula actually to derive something we can actually implement and that doesn't require a heptadian people. So there will be a lot of assumptions. I'm going to try to make them very explicit, even more explicit than the textbook, because sometimes they just jump over things without making the assumption explicit, but I'll try to be very making it explicit to you. So what abstraction are you going to take? Well, we can take sets, bags, or lists, right? We saw we can either abstract documents as sets of words or lists of words or bags of words. Well, today, I'm going to assume that documents are sets of words. I don't care about term frequencies, a bit any of this. I just see documents as vectors of Booleans, sets of words, okay? So it means that my small d and my small q, d is a specific book, it's a mathematical variable, so d might be the book information retrieval, and it's a vector of Booleans. There is a 1 for every term that the book contains, and there is a 0 for every term that the book does not contain. The vector might be 500,000 in height, right? Because it's all the terms that you can have in the book. So it's a very, very large vector with 500,000 entries in there. And D1, D2, D3, these are again mathematical variables that can be 1 or 0, right? And 1, 2, 3 is just an enumeration of the terms. I could also have called it D information, D retrieval, but instead I call it D1, D2, D3 with numbers. The same with my query. Now, of course, the query will be sparse because the query probability has only, in that case, 2 terms. So there's going to be 0 everywhere and a 1 for information and a 1 for retrieval, right? And again, beware that this is a small d, this is a small q, it's a small d1, small q1. It's mathematical variables. You can literally replace them with actual zeros and ones. Right? And small d and small q, you can actually replace them with vectors of actual Booleans, right? These are not random variables. Okay, who's with me? Okay, so now what I could do is define random variables, but not for the whole document, just for one term. So I could define a random variable that I called big D ETH that assigns every one of my heptadian rooms to either a 0 or a 1, is going to be a 1 in the rooms in which the document contains the term ETH, and it's going to be a 0 in all the rooms in which the document did not contain the term ETH, right? So it's a 1 or a 0. And this little d ETH, you can set it to 1 or 0 as you wish, okay? You can do the same with the query. You can define the random variable big Q information, that is a function that assigns every room with a 0 or a 1. It assigns the rooms with a 1 in which the query contains information, and it assigns the rooms with a 0 in which the query did not contain information. And this little q information, again, you can set it to 0 or 1, right? So now that we have these new random variables, big D indexed by a term and big Q indexed by a term, I can also write that formula, right? Who agrees that this formula makes sense, right? So if I take a specific small q, it's a query, for example, information retrieval, and I take a specific k, for example, k could be ETH, right? If I take a small k and a small q, then I can write this down, and this gives me a number that spits a number, right? It's the probability, if I only consider the rooms in which they said yes, and in which the query that was given to them was little q, information retrieval, then I compute, I look at the rooms in which the document contained ETH, right? If dk is 1, if small dk is 0, then I look for the queries, the rooms in which the document did not contain ETH, and then I do my fraction, right? I do my division to find out that number. Okay, so again, this small d is either a 0 or 1. If it's a 1, you're looking at the probability that the document contains k. if small dk is 0, then you're looking at the probability that it does not contain term k. Now, here's the assumption we are going to make. We are going to assume if I compute the probability of a specific document small d, we are going to assume that the terms appear independently of each other in the document. It's a big assumption, right? What does it mean independent? Remember that then the probability becomes a product. So basically, the probability that it is my specific document is a product over each term, right? It's basically, for example, imagine I take the document as a very small book with just 2 words, information retrieval. Then it's going to be the probability that big D information is 1, multiplied by the probability that big D information retrieval is 1, and then multiplied by the probability for all of the other terms that they are 0. But of course, this might be hard to digest, so I have an example, makes it a bit easier. So imagine that we have a document small d that says Polyban is unexpectedly working today. So I heard from you that it was some meme among students. So let's say small d Polyban is unexpectedly working today. Small d is a vector of Booleans, and I put my vector of Boolean on the right in yellow, right? So d Polyban is 1, d is 1, d unexpectedly is 1. These are all the words that are in there. And Zurich, ETH information, it doesn't appear in there in small d, so it's a 0, right? So you agree you have a vector in there. I just reordered it starting with the terms that are in the document, right? Who agrees on the right that this is a document and a vector of zeros and ones? Okay, great. So now, how do I compute the probability that my document is Polyban is unexpectedly working today? I'm saying it's a product. It's the probability that it contains Polyban multiplied by the probability it contains is, multiplied by the probability it contains unexpectedly, and so on and so on. And then multiplied by the probability it does not contain ETH, it does not contain Zurich, it does not contain information, and so on, right? And the reason I can do a product is because of my assumption. If I assume that the terms are all independent from each other, I can just compute a product like that. For whom does that make sense? Right? Just a big product. And when I write here my small dk, it's again because sometimes it's a 0, sometimes it's a 1, right? So this is what I have in there. And k would be Polyban is unexpectedly and so on, right? So I can rewrite it that way. Now you see the small k is actually a term. Yes? The order, no, we do not care about the order of the terms. And the order of the terms in the vector is arbitrary. I just count them like this is the first, this is the second, completely arbitrary, right? And again, this is because we have the set of word semantics, right? Originally, the document is a list, but I forget about the order in the document. So do you agree that because multiplication is commutative, you see that you're going to get the same result even if the document was unexpectedly working today is Polyban, right? Or if you want to talk like a Jedi Master, today, unexpectedly working Polyban is, right? And that would give you exactly the same multiplication because it doesn't matter in which order it is, right? Does that make sense? Okay, awesome. So you see that this small d is really something that I can put whatever inside. I can put zeros, I can put ones, and big D is any vector that I take. It's the current document that I'm evaluating. Okay, and now I can replace these ones and these zeros with the small d, but the small d's are on the right, right? If you take d Polyban is actually 1, d is actually 1, and so on. So do you see this big product on the left? The probability that for every term, the big D, so the random variable, is equal to the small d, that's the same formula as I have here. That formula here, just look at this one if you're confused, right? And never forget that the small d is a mathematical variable. It's an actual value that you can put in there. In that case, this one. Okay, so this is the assumption we make. We can just multiply over the terms because it's all independent. Now, going back to the trick that we want to use, we want to rank this ugly thing right here, probability that R is 1 given that B is a specific document and the query is Q. And I would do it for every document 1,000,000 times. I would compute a billion times, even a billion of those. I sort to find the highest probabilities, and I'm going to return the highest ones, right? The F and D in that case would come first, and then G, and then E. Okay, now, How do we do that? Well, it's a bit like the umbrella in the rain, right? I'm looking for the probability of relevance. It's a bit like the probability that there is extraterrestrial life, right? It's very hard to estimate. So let's use the base formula. Usually it works, right, when it's hard to estimate. So let's use the base formula. For example, if I would use the base formula in that way, the probability of relevance given a document, I can just swap. Now it becomes the probability of a document given the relevance, and then with the correcting factors. This is just the base formula, right? Exactly as it is. Now you know that when I have a formula like that, it's okay to add a condition everywhere, the same condition everywhere. So it's okay if I add Q everywhere. So I condition everything on the fact that query is Q. It's just that you're zooming in on the specific query you're looking at, but that formula is still true. Okay? So now, if I do that, maybe I will find a way of simplifying this to the point that it becomes implementable. But there's a bit of work to do, and now we're going to work on that. It's like one of these cooking shows where you see people preparing the recipe in front of you. So we are going to do some cooking, but the ingredients will be mathematical objects. Okay? All right. So can we get rid of some of it? Of course we can, because this is why we are here. So here's what we are going to try to do. So I just put it slightly higher. Right? So this is my formula. Now, do you agree that I can write exactly the same thing, but with R equals 0, right? That's fine. It's exactly the same rule and so on. So I just write it down on top of each other. And now what I could do is I could do a division. Do you see that this is the complement of that within the document and the query being that? Do you see that these are complementary to each other, right? What do I get if I compute the ratio of the probability of an event divided by the probability of its complement? Do you remember? It's the odds, right? So if I do that divided by that, I get the odds of relevance, and I just need to divide this. So I need to divide 1 over 0, right? The probability of the events divided by the complement. Now, here, what is up there is the first one. What is down there is the second one. So now I can replace this with this, and I can replace that with this. So we can do it now. But you see what happened? I only have here this product here, and I dropped that. And below, I have the product here, and I dropped this. But do you see why I dropped it? Because it's the same, right? So if I divide two things, but they have exactly the same denominator, I can let go of it. So we already got rid of 1/3 of the ugly thing, right? We already got rid of the denominator now. Okay, who's with me? Okay, and we are just going to continue to simplify like this. Now, this division here, sorry, this is what went away, just to say because it's the same. So now we are at this. Now, remember what I told you about the odds. It's an increasing function. So do you agree that if I sort by probability of relevance, it's the same as sorting by the odds of relevance, right? The probability is higher, the odds are higher. So it doesn't matter if I sort the odds or the probability. So now I'm back to the problem of sorting this, right? The odds of relevance. Now, I can just, because of commutativity and associativity with multiplication division, I can split it like this. What is the probability of R equals 1 divided by R equals 0? It's again the odds, right? These are also odds. It's the odds that it's 1 considering the query. Okay. Now, the next thing is that because with the magic of the base formula, I swapped the whole thing, I now put the relevance on the right and the document on the left, because I swapped them. That's the magic of the base rule. Now I'm computing the probability that the document is small d. Small d is, for example, the book information retrieval. Do you remember how we said that this probability that big D is a specific document? If I rewind, we made this assumption right here that we can replace it with a product, right? So the probability that it's this specific vector small d can be replaced with this product, or this right here, right? Just the visual of doing that. So now my probability that big D is a specific vector can be replaced by this huge product, It's a product with 500,000 factors because it's over all of the terms that I have in my collection. So let's do exactly this, but in the formula in which we were. So now I'm just going back to where we were. We were here. So now I'm going to replace this probability that big D is a specific vector with the product, like this. So if I replace it, this is what I get, right? The probability that D equals small d, conditioned on R and Q, is the product that the individual components, so the random variables corresponding to the individual coordinates, match the decays of my document. The decays are the zeros and ones specific to my book. And I still have this condition on R and Q, but again, it's the same thing I did earlier. Whenever you have a formula, it's fine to add everywhere the same condition, right? So it's exactly the same thing. I'm just adding everywhere that it's conditioned on being relevant and the query being whatever Alice typed in front of her computer. All right? So now I'm going to take that and plug it back into our formula right here. If I plug it back, I get this, right? All I did was replace it with a product. Who is with me? Okay. So now I have this product. Do you agree that because it's commutative and associative, I can do that, right? I can just take the product out. It's just that the division of the products is the same as the product of the fractions, right? Okay, so now I have this. Now, remember that this small dk, for every value of k, it's a 0 or it's a 1, right? This is really a mathematical variable. So do you agree that dk, for example, could be this? So what we are going to do, because we are looking at a specific document, for example, this one, what I'm going to do is I'm going to split right here, like this, because I'm looking at a specific document. So I'm going to put on one bucket all of the terms for which this is 1, and then in another bucket, all of those for which it's 0. In other words, I'm splitting my product like this. And it might be more obvious if I showed you this. This is how I'm splitting my product. I'm having the product for which it's 1 times the product for which it's 0. Who is with me? Okay, this is exactly what I'm going to do now, but using scary mathematical symbols. So this is where we were. I'm just splitting it with the part where it's 0, that was the lower part that I showed you, and the part where it's 1, which was the upper part, right? Of course, the split depends on the document that I'm looking at, right? But I'm looking at a specific document. This small d is a very specific one. So I'm splitting like this between the terms that don't appear and the terms that appear, right? And you saw that since they're all 0, then I put a 0 in there because it's always 0, and I put the 1 in there because it's always 1. Okay. Now, we're going to give names to these things. So I'm going to call this thing P, and it depends on the query and on the term. So I have a K and a Q in the subscript, right? So I'm going to call it PKQ, sounds like Pikachu. It's easy to remember, like PKQ. And now I have UKQ, right? Okay, it's basically the probabilities that term K is in the document. Up there, it's conditioned by relevance, and down there, it's conditioned by non-relevance, right? And then I can put, that's called the contingency table, right? That's all the possibilities. Either my document is relevant or not. And then based on relevant or not, I can have a probability that the K term is present, K is a specific term, or that it's absent, right? So you see, I'm conditioning on a row, conditioned on the fact that I'm on that row. I have a probability of Pikachu that the K term is present, and a probability of 1 minus that it's absent, right? Because we're conditioning on that. So you agree that this is PKQ, this is UKQ. I did the same thing here. That's condition on R equals 0. So I'm here, that's UKQ. All right. Do you agree that this thing right there is in fact 1 minus Pikachu, right? It's a 1 minus, oh, sorry. And this is here, 1 minus also. So I'm going to be able to reuse these on the left. So this is why I only give names in there. Now, we make more assumptions. And I'm going to warn you, some of the assumptions might be a bit courageous, sometimes kind of hand-wavy, like, okay, we're going to assume this or that, just because it simplifies things. One of the assumptions, and you can have a whole debate or troll the internet whether that's actually relevant or not, but what people actually say is that we're going to assume that for the terms that are not in the query, so K, if QK is 0, for the terms not in the query, P and U are the same, right? So it means that for all the terms except information and except retrieval, if my query is information retrieval, I'm going to assume that the term I'm looking at, for example, butterfly or ETH or building, its presence in a document, it doesn't depend on the relevance. Why? Because the term is not in the query. Something totally unrelated, like computer or butterfly or room or whatever. So we make the assumption that in the case that my term is not in the query, which is almost all of them, this is the same. These two numbers are the same. Again, you can agree, you can disagree, we can talk for hours whether that makes sense or not, but it's an assumption that we are making, right? So if we do that, we assume that these are the same. What's going to happen is that these are the same. So you divide something by the same thing. What do you get? 4 divided by 4 is 1, right? So this is always 1. So since you made the simplifying assumption that for the terms not in the query, this is the same, you're going to get a 1. So what it means is that we can take out of the product everything that's not in the query. Because for all the terms that are not in the query, the quotient is a 1. What it means is that I just add on the product that I'm only multiplying over the terms in the query. In my case, only about information and retrieval. That is a much smaller product, right? Okay. I suspect that this was on purpose, that the people asked them, okay, how could we restrict to only the query? Well, if we did assume that when it's not in the query, it's the same, then that goes away. So let's make it go away, right? So sometimes you can also do the reverse reasoning, right? But technically, an argument can be made that for the terms not in the query, we can strike this out because these two numbers are the same. So this is now we have the much smaller product that we only multiply on the terms that are in the query. It's very similar to evidence accumulation in the ranked retrieval, where we only, it seems like a huge scalar product, but in fact, you only add over the terms that are in the query. So the same sort of things happens here, right? Okay, so that's the first assumption. We throw away everything that's not in the query. Next assumption, we are going to drop the Q subscript. We are going to assume that these probabilities that the terms appear or not in the documents, that doesn't depend on the query. It only depends on K. That's also a very courageous assumption. I mean, you can argue, you can have a debate for hours whether that makes sense or not. But basically, we can make this assumption, simplifying assumption, that we drop the subscript Q because that table of probabilities would not depend on the query. If you do that, you can just drop the Q and that's it, right? It's yet another assumption that you can agree or disagree with. Okay. Now, I'm going to replace this with PK and UK, right? So if I write it that way, I think I swapped the two. The one on the right is on the left, the one on the left is on the right. Not sure why I did that. But basically, this is PK divided by UK, which you have on the left, and then 1 minus PK divided by 1 minus UK. You see that it's 1 minus, right? Because if PK is D equals 1, then D equals 0 is 1 minus. It's the complement. Right, so this is why when I have D equals 0, I can just put the 1 minus instead. Okay? Who is with me? We're just trying to make up assumptions to simplify this full formula. That's really what we're making. Offline, you can again go over and see that all the steps make sense. Now, we have here the terms that are in the document. That was my upper part in the Polyban unexpectedly working thing. That was my upper part. The terms in the document. And on the right, I have the terms not in the document. Now, do you agree that if I multiply something by a certain number, and I also divide it again by that same number, that I didn't change it, right? I'm going to do exactly that. And I can do it with any number, right? With any number. So let's do it with that ugly thing right there. So I'm going to divide, sorry, I wanted to get up there. I wanted to divide with this thing. And you agree that I can also multiply here with exactly the same thing. If I divide and multiply with the same thing, that doesn't change the quantity. So I'm going to do that. And when I do it, it slightly changes because if you think of what's going on, if you divide by this, you end up with this, right? I just plugged, since you divide, you need to swap up down, right? So you end up with the 1 minus k from below ends up there, the 1 minus pk ends up there. What can I do this? It's exactly the same condition here in my product, right? So I'm just using the commutativity of the product, right? It's exactly the same condition. So I put them pairwise. This divided by this gives me that. Now I multiply with the same thing. Do you see that now I have a product over the terms that are not in the documents, and then the product over the terms that are in the documents. It means that I'm summing over all terms, right? If I'm basically reunioning the upper part and the lower part here. So it means that I drop the condition over decay because now I have them all again. It's exactly the same thing we're multiplying. So it means that here I only condition on the other one, qk is 1. So now over the fact that the terms are in the query. So now I end up with this. But now there is something super cool that happens, is that this part on the right doesn't depend on the documents that I'm looking at. How can you tell? There is no D in there. You can look all you want, there is no D anywhere. Remember what we are trying to do. We are trying to sort these numbers by documents. We want to sort them. But now on the right, I have some constant factor that is the same for all documents. It's really a constant, right? It might depend on the query, but for a given query, it doesn't affect the ranking of the documents. So do you agree I can drop it? Right? I'm just dropping a constant factor regarding the documents. So that goes here. Drop. This is all we care about. So I end up with this, this becomes more implementable now. It's a small multiplication because I'm only multiplying over the query terms. And I only need to multiply some these things that come from my contingency table. Now, do you agree that if I take the log, it doesn't change the order, right? So I can take the log of that, right? So if I take the log, I end up with basically this reformulation. And now you realize that P over 1 minus P, that's an odd, right? It's the odds that term K is in the document and given relevance, and the odds that term K is not in the document given the relevance. Okay, now you know that the log of a division is the same as the subtraction of the logs, right? Log of A divided by B is the same as log A minus log B, right? Just the rules of logarithms. So I end up with this. Now, these are the odds of containing term K in relevant documents, and these are the odds of containing term K in non-relevant documents. And again, the PKs and the UKs, I can no longer say Pikachu because we got rid of the Q now, but this is my contingency table. So assuming for every term I have a contingency table like this, I can compute this thing. That's called the retrieval status value. And all I need to do is sort that by document and I get my results. But I still need to get the rabbit out of the hat. So this sum here is technically a sum of weights, right? That only based on the term. So this could be re-expressed as the sum of CKs. It's a sum of weights. But that should sound very similar to something we've already seen, right? When we have done these scalar products to do the ranked retrieval, remember, with all the parameters, right, with the zones. So technically, we have these weights, CK, it's a weight for every term, and I'm just summing over the terms that are in the query and in the documents. It's exactly the same pattern that we had in the vector space model with the scalar product. We are summing the TF-IDFs for the term in the query and in the documents. We can either do it term at a time or document at a time. So that is a very similar pattern, right? It's really very similar to what we've seen before. Okay, so now we basically have something really fantastic that looks incredibly close to what we've implemented so far, even with the standard inverted index. We just need to compute the sum of some weights over the terms that are in the query and the document that I'm looking at. And then I sum over that, okay? And the only thing that remains to be done, but I'll not do it today because it's 12, is how do we find out this PK and this UK, right? It will need more assumptions. And I think it's very daring, I think, the assumptions that they are making here. And I suspect that they are made in such a way that it simplifies, but it actually works. So I'm only going to pull the rabbit out of the hat next week. But basically, I can tell you a bit of a cliffhanger, but you can think about it. Technically, what's going to come out of that is the IDF. We're going to end up with a sum of IDFs. And basically, that plugs us back to the vector space model, because what's happening is that if we start with these heptilion people in Antarctica and derive a few mathematical formula, we end up summing IDFs. So it means that the whole thought experiment with the people in Antarctica justifies why we are using the IDF in our terms in vector space model. That is how it closes the loop, right? Okay, so I'm going to stop here. There's not so many slides left, but I'll finish that next week. Read the textbook if you want, but I have to give you a word of warning. In the book, they use these formulas that I told you not to use. So you will find probability of small x and so on. But since I showed you how it's done the right way with the explicit random variables, hopefully that will make it easier for you to understand what's going on in there. Okay? So you made it. I warned you, this is already master's level, but I spent 1 hour reminding you of the probability theory. So I hope you learned one thing or two, that it was a good refresher for you with probability theory. And now you see the sort of things that you can do when you ask a heptilion people in your thoughts, and you can actually derive a system that you can implement in practice. Right. So thank you very much. Enjoy the exercises that the TA team prepared for you. And I'll see you next week. We're going to finish that, and then we'll start looking at language models. Right? So enjoy the rest of your day. Have a good weekend, and see you soon. Thank you, Marco, for moderating.